Exercise 1. The task here is to determine the electric field created by a segment of wire of length L carrying a linear charge density lambda at a point P located on the medium plane of the wire. So how should you start with a question like this? So the first step is always to draw a diagram, just to figure out what's going on. And then once you've done that, you want to draw another diagram to represent the electric field, which you should be able to resolve into x and y components. You then need to figure out an expression for a tiny chunk of the electric field. So the electric field coming from a tiny bit of the length of wire. It's then useful to figure out which components of the field you're interested in, as you might not need to do the calculation for all components if some of them aren't relevant. And you then want to write an expression for a sum of all the tiny chunks of electric field to find the total electric field at the point P. So you would then calculate the summation, which will probably be an integral, and then try and simplify it as much as possible. So let's start with the answer to exercise 1. Here is our wire of length L and charge per unit length lambda. And here is our point P, at which we want to find the total electric field due to the wire. This is a distance of x perpendicular to the centre of the wire. Let's label the top of the wire L over 2 and the bottom of the wire minus L over 2. Now, to find the electric field due to the whole wire on point P, we need to split the wire into tiny segments, find the field due to each of these segments, and then add them up. So here I will draw on one of those tiny segments dy. This segment that we've chosen at random is at a length r from point P and at an angle of theta. You can see that r will be different as we move down the wire for each different segment, which shows that the electric field from each segment will not be the same at point P. The distance of the segment from the centre of the wire we can label as y. So y will change as we move down the wire looking at all the different little segments. To visualise the electric field from this segment, you can draw out the electric field diagram. The electric field from that segment is directed down along R to point P, with components in the x and y directions. We can now work out the electric field due to this tiny segment, which will be given by this equation. This comes from the equation for the electric field due to a point charge. We assume that dy is so small it's effectively a point charge. Then you can see that we have given the charge as lambda dy. The charge per unit length lambda times the length dy will give the charge in that tiny segment. The cos theta I gives Ex, which we can see from the electric field vector diagram, where cos theta equals Ex over the length of E, and the sine theta j gives the y component. Just to recap, dE is the tiny bit of electric field at point P due to the tiny length of charged wire dy. Now, looking at the diagram, we can see by symmetry that the y components of the electric field will cancel out when we add up the contributions from the whole wire. What we mean by that is that the top of the wire will produce an EY at point P that is pointing down, and that is quite big. As we move down the wire, the EY produced by that section of wire gets smaller until at the midpoint of the wire there is no EY component at point P. Then as we move into the lower half of the wire, there is a small component of EY pointing upwards, which gets bigger until we reach the bottom of the wire. So when we sum up the EYs from the whole wire, the bottom half will cancel the top half and we will have no EY overall. There is no electric field going up or down at point P, so there will be no force up or down on a charge which was placed at point P. If we did put a charge at point P, it will be pushed left or right, but it will not be pushed up or down. And that makes sense because point P is in the centre of the wire. Think of it as if the top section of the wire is pushing a charge at P downwards, diagonally, then the bottom section will be pushing it back up diagonally. So it wouldn't move up or down, only left or right. So that was quite a long explanation about why we're going to get rid of the EY component from our equation. That just leaves us with the EX component, and we want to add up the EX components from the whole wire, so we need to do an integration. We can't just find the EX component from one tiny bit of wire DE and multiply it by the whole length, as the EX component changes as we go down the wire. That's why we need to do an integration. You could, if you wanted, just integrate to the midpoint and then double your answer, as the top half of the wire will contribute the same as the bottom half by symmetry. But here I've just integrated the whole thing so that our limits are from minus L over 2 to plus L over 2. So why don't the EX components cancel out? Well, the EX vector from the top half of the wire will point to the right, as in our electric field diagram, and the EX component from the bottom half of the wire will also point to the right. This is different to the EY components, where in the top half of the wire they pointed down, but in the bottom half they pointed up and so cancelled. As we are writing EX now, we don't have to include the I, as the X in EX already tells us the direction. That's why the I has disappeared. So now we have the integral we want to calculate, but the problem is that it integrates over y, but the things in the integral are not written in terms of y. So we could rewrite the cos theta and r squared in terms of y, but in this case it turns out that it's easier to write everything in terms of theta. So let's work out all the parts in terms of theta. We can see from the diagram that y equals x tan theta. Differentiating that gives us dy, and then r squared is x squared plus y squared, and subbing our formula for y in terms of theta gives us this. We don't need to put x in terms of theta because here x is a constant. It doesn't change as we move down the wire, so x is the same for every single segment dy. So we can simplify the r squared like that. So subbing all of those in to our integral gives us this. And we now need to give the limits in terms of theta as well. We'll work those out in a minute. We'll just write theta at L over 2 and theta at minus L over 2 for now. And now the reason for putting it all in terms of theta becomes clear. We can cancel the x squared theta to give this. We've also moved the x out of the integral as it's a constant. Doing the integral is now simple and gives this. We now need to work out what sine theta is when theta is at its maximum and minimum points. Looking at the diagram, we can see that sine theta equals y over r, and y at the top of the wire is L over 2, and r is given by this, and y at the bottom of the wire is minus L over 2 with r given by the denominator there. Putting these into our equation for Ex gives a final answer for the electric field at point P due to the charge wire as this. Okay, some things that students have found confusing about this exercise. First thing is that we are finding dEx and integrating over dy. So they're confused about why one is in the x direction and one is in the y direction. That's because we are finding the x component of the electric field for a little tiny bit of the wire, and then moving down and finding the x component of the electric field for the next bit of wire, then moving down in the y direction and finding the x component of the electric field for the next bit of wire. Another thing is that x is a constant in this example. And another thing which has confused people is that some students thought that the top half of the wire was positive and the bottom half negative, which is not the case. I think they were confused because we labelled the bottom of the wire as minus L over 2, but that is just the position of the bottom of the wire on the y-axis. And another thing that confused students is why the EY component's cancelled, which is why I tried to give a clear explanation of that in this video.